Hi guys, welcome to ENS181 Engineering Mathematics. In this video, we're going to discuss the application of first-order ordinary differential equation as a mathematical model to solve some of the practical engineering problems. So here's the chapter contents of our discussion. We're going to discuss first the linear models, then the nonlinear models. For linear models, we have growth and decay, half-life, carbon dating, Newton's law of cooling or warming, mixtures, and electrical circuits problem. First, we have the growth and decay. So we have this differential model for growth and decay, which translate as the change of population or amount of a specific substance with respect to time is directly proportional to the amount of substance or the population present at that specific time. So we have an initial condition here. So at time t equals to 0, we have the initial value of our population or the amount of the substance. So our constant of proportionality k here will determine if we have a growth or decay problem. So if the value of our k is less than 0, then we have a decay problem. And if the value of our k is greater than 0, we have a growth problem. So to apply this differential model, we have here an example. A culture initially has p sub 0 number of bacteria. At t equals to 1 hour, the number of bacteria is measured to be 3/2 of the initial population. If the rate of growth is proportional to the number of bacteria p of t present at time t, determine the time necessary for the number of bacteria to triple. So this one is a growth problem. So first we have to gather the data present on our problem. So we have at t equals to 0, the amount of bacteria present is p sub 0. And after 1 hour, the amount of bacteria present is 3/2 of the original population. So applying our differential model, we have dp over dt equals to kp. So we change the variable x with p since we are dealing with the population of bacteria. So to apply these initial conditions, we have to solve first the solution of our differential model. So this one, we have a variable separable. So to solve this, we have dp over p equals to k dt. Then we integrate both sides. We have ln of p equals to k t plus c. Applying exponential both sides, we have e raised to ln of p equals to e raised to kt plus c. Simplifying this one, we have p equals to e raised to kt times c. Since e raised to c is just a constant. So this one is our solution for this differential equation. But first, we need to identify the value of our arbitrary constant c and the constant of proportionality k. So to find the value of our c, we are going to apply our initial condition. So at t equals to 0, we have e raised to k 0 times c. So p of 0 natin is the initial value of our population. So e raised to 0 times c. So the value of our arbitrary constant is p sub 0. So our solution now, p of t is equal to p sub 0 e raised to k t. So next, we have to find the value of our variable k. So we are going to apply this second condition. So at t equals to 1r, the value of our population is 3/2 of the original number. So we have 3 over 2 p sub 0 equals to p sub 0 e raised to k times the time is 1. So cancel si p sub 0, we have e raised to k equals to 3/2. So solving for k, we apply natural logarithm ln to both sides of our equation. So ln of e raised to k is just equal to k. Then ln of 3/2 is 0.4055. So now our population p of t is equal to p sub 0 e raised to 0.4055 t. So now we can find what is asked on the problem, which is to determine the time necessary for the number of bacteria to triple. So the number of our bacteria, p of t, will be 3 times the initial value of the bacteria, equals to p of 0 e raised to 0.4055 t. So we have to find the value of t that takes the number of bacteria to triple. So cancel si p sub 0, we have e raised to 0.4055 t equals to 3. Applying again natural logarithm to both sides of the equation, we have 0.4055 t equals to ln 3. Solving for t, we have ln 3 divided by 0.4055. The answer is approximately equal to 2.71 hours. So it takes 2.71 hours, that makes the number of bacteria to triple. Next, we have the half-life. So half-life is a measure of the stability of radioactive substance. The half-life is simply the time it takes for 1/2 of the atoms in an initial amount A sub 0 to disintegrate or transmute into the atoms of another element. So the longer the half-life of a substance, the more stable it is. So for the differential model, for solving the half-life, we have this one. The rate of change of substance with respect to time is directly proportional to the amount of substance present at that specific time. And we have the initial condition at t equals to 0, the amount of substance is A sub 0. So to apply this differential model, we have an example here. A breeder reactor converts relatively stable uranium-238 into the isotope plutonium-239. Then after 15 years, it is determined that 0.043% of the initial amount A sub 0 of plutonium has disintegrated. So find the half-life of this isotope if the rate of disintegration is proportional to the amount remaining. So we have here, at t equals to 0, the amount of substance present is A sub 0. Then, after 15 years, at t equals to 15 years, the amount of substance present is 0.043% of the initial amount of plutonium has disintegrated. So this is the disintegrated amount of the substance. So what's left of that substance after 15 years is 0.99957 A sub 0. So this is the amounts left after 15 years because only 0.043% has disintegrated. So we're going to apply our differential model. We have dA over dt equals to Ka. So same with the growth decay, this one is an example of a decay problem. So we have a variable separable equation here. So solving for the solution of this differential model, we have dA over A equals to K dt. Integrating both sides, we have ln A equals to Kt plus C. Solving for A, we apply exponential to the both sides of our equation. We have A of t equals to e raised to kt times C. So to find the value of our arbitrary constant C, we have to apply our initial condition. So this is the solution for our differential model. So applying our initial condition, we have at t equals to 0, the amount of substance is A sub 0 equals to e raised to k times 0 times C. So our arbitrary constant now is equals to the initial amount of our uranium-238. So our solution now, A of t is equals to A sub 0 e raised to kt. So now to find the value of our k, we're going to apply this second condition. So at t equals to 15 years, the amount left of our uranium-238 is 0.99957 A sub 0 equals to A sub 0 e raised to k times 15. Cancel si A. Solving for k, we have e raised to 15k equals to 0.99957. Applying natural logarithm to both sides of the equation, we have 15k equals to ln 0.99957. Then solving for k, we have the value of k is negative 2.867 times 10 to negative 5. So we have a negative value of k since it is a decay problem. So our final solution here, we have A of t equals to A sub 0 e raised to negative 2.867 times 10 to the negative 5 t. So we can now use this solution to find what is asked in the problem, which is the half-life of the isotope uranium-238. So half-life, it means that the amount of substance present is half of the original value. So 1/2 a sub 0 equals to a sub 0 e raised to negative 2.867 times 10 to the negative 5 t. Cancel sa a sub 0. Then applying ln both sides, we have ln of e raised to negative 2.867 times 10 to the negative 5 t equals to ln 1 over 2. So we have negative 2.867 times 10 to the negative 5 t equals to ln 1 over 2. Solving for t, we have ln of 1/2 divided by negative 2.867 times 10 to the negative 5 is approximately 24,177 years. So the half-life of the isotope uranium-238 is approximately 24,177 years. Next, we have the carbon dating. So the theory of carbon dating is based on the fact that isotope carbon-14 is produced in the atmosphere by the action of cosmic radiation on nitrogen. So the ratio of the amount of C14 to ordinary carbon in the atmosphere appears to be constant. And as a consequence, the proportionate amount of the isotope present in all living organisms is the same as that in the atmosphere. So the method is based off the knowledge that the half-life of radioactive C14 is approximately equal to 5,600 years. So we are able to identify the age of an object or of fossils as long as we know the value of the radioactive C14 present on that object. So to apply a differential model for carbon dating, we have an example here. So a fossilized bone is found to contain 1,000th of the C14 level found in living matter. So we have to estimate the age of the fossil. So what we know is that at t equals to 0, the amount of C14 is equal to a sub naught. Then at t equals to 5,600 years, the amount of C14 is 1/2 of the original value. So for this one, it is an example of a decay problem. So we can use the differential model dA over dt equals to Ka. So we already know the solution for this kind of differential equation, which is A of t equals to a sub 0 e raised to kt. So we need to identify the value of our variable k. So we're going to use this half-life of the C14. So at t equals to 5,600 years, the amount of C14 present is 1/2 of the original. So we have 1/2 a sub 0 equals to a sub 0 e raised to k times 5,600 years. Cancel sa a sub 0. We have e raised to 5,600k equals to 1/2. Applying ln both sides of the equation, we have ln of e raised to 5,600k is just equal to 5,600k. Then equals to ln 1/2. Solving for k, we have, so the value of k is negative 1.2378 times 10 to the negative 4. So our complete solution a of t now is equal to a sub 0 e raised to negative 1.2378 times 10 to the negative 4 t. So now we can use this to find or to estimate the age of the fossil. So it says that 1,000 of the C14 is present on the fossilized bone. So it means that 1 over 1,000 a sub naught is present. So we have a sub naught e raised to negative 1.2378 times 10 to negative 4 t. Cancel si a sub naught. So, solving for t, we have e raised to negative 1.2378 times 10 to the negative 4 t equals to 1 over 1,000. Applying ln to the both sides of our equation, we have t equals to ln of 1 over 1,000 divided by negative 1.2378 times 10 to the negative 4. So, the estimate age of the fossil is approximately equal to 55,807 years. So this is the estimate age of the fossil. Next is the Newton's law of cooling or warming. So the Newton's law of cooling, which is equally applicable to heating, states that the time rate of change of the temperature of the body is proportional to the temperature difference between the body and its surrounding medium. So if we let capital T denotes the temperature of the body and we let T sub m denotes the temperature of the surrounding medium, then the time rate of change of the temperature of the body is equal to d capital T over dt, and the Newton's law of cooling can be formulated as this one. D capital T over dt equals to negative k times the quantity T minus Tm. So, rearranging this, we have this differential model, which is a linear differential equation, where k here is a positive constant of proportionality. So once k is chosen positive, the minus sign is required in Newton's law to make the rate of change negative in a cooling process, when the temperature of the body is greater than the temperature of the surrounding medium, and positive in a heating process when the temperature of the body is less than the temperature of the surrounding medium. So we have here an example. A dead body was found within a closed room of a house where the temperature was at a constant 70 degree Fahrenheit. And at the time of discovery, the core temperature of the body was determined to be 85 degree Fahrenheit. Then 1 hour later, a second measurement showed that the core temperature of the body is 80 degree Fahrenheit. So assume that the time of death corresponds to T equals to 0, and that the core temperature at that time was 98.6 degree Fahrenheit. So we have to determine how many hours elapsed before the body was found. So we are going to act as a detective. So what we know from the problem is that we have the temperature of the surrounding medium, which is equal to 70 degree Fahrenheit. So at T equals to 0, the temperature of the body was 98.6 degree Fahrenheit. Then at time of discovery, X, the value of the temperature of the body was 85 degree Fahrenheit. Then a second measurement after an hour from the discovery shows that the temperature of the body was 80 degree Fahrenheit. So we have variable X for the time of discovery and X plus 1 for the time of the second measurement. So for Newton's law of cooling and warming, our differential model is the rate of change of temperature with respect to time is equal to negative K times the difference of the temperature of the body and the temperature of the surrounding medium. So rearranging this one, we have dt over dt plus kt equals to ktm. So we have a linear differential equation. So our p of t here is equal to k, and our q of t is equal to ktm, which is the value of our tm is 70. So we have 70k. So solving for our integrating factor I, we have e raised to integral of p of t, which is k dt. So the integrating factor I is now equal to e raised to kt. Applying this for the formula for the solution of linear differential equation, we have integral of d times t times e raised to kt equals to integral of our qt, which is 70k, times the integrating factor, which is e raised to kt dt. So the integral of the left-hand side of our equation is just equal to t e raised to kt. Then the integral on the right-hand side is just equal to 70 e raised to kt plus c. We just apply that we let u equals to kt and our du is equals to k dt. So you'll get 70 e raised to kt plus c. So dividing whole equation by e raised to kt, we have the temperature at any specific time is equals to 70 plus c e raised to negative kt. So this is the solution for our differential equation. So we have to find the value of our arbitrary constant c. We're going to apply this first initial condition, which is at t equals to 0. So at t equals to 0, the temperature of the body is 98.6 degree Fahrenheit. So this is equal to 70 plus c e raised to negative k times 0. So this one is equal to 1. So we have c is equal to 98.6 minus 70, which is 28.6 degree Fahrenheit. So now we have the value of our arbitrary constant C. So our solution P of T is equal to 70 plus 28.6 e raised to negative kt. So we're going to use this to find the value of our x, which is the amount of time elapsed before the body was found. So we are going to apply at t equals to x at time of the discovery. So at time of the discovery, the temperature of the body is 85 degrees Fahrenheit, which is equal to 70 plus 28.6 e raised to negative kx. Simplifying this one, we have e raised to negative kx equals to 85 minus 70 is 15 divided by 28.6. Solving for kx, we apply natural logarithm to the both sides of the equation. We have negative kx equals to ln of 15 over 28.6. So it is equal to negative 0.64536. So kx here is equal to 0.64536. I just divide the whole equation by negative since we have negative kx here. So we have this one, our first equation. Then, at the second measurement, the temperature of the body was 80 degrees Fahrenheit. We have 80 degrees Fahrenheit equals to 70 plus 28.6 e raised to negative k times the time is x plus 1. The time of discovery plus 1 hour. So simplifying this equation, we have e raised to negative k times x plus 1 equals to 80 minus 70, we have 10 divided by 28.6 degree Fahrenheit. So applying again natural logarithm to the both sides of equation, we have negative k times x plus 1 equals to ln of 10 over 28.6, which is equal to negative 1.05082. Distributing k and dividing whole equation by negative 1, we have kx plus k equals to 1.05082. So this one is our second equation. So we have the value of kx, which is 0.64536. We just substitute that here. So the value of our k now is equal to 0.40546. So this one is the value of our k. Substituting that here at kx so that we can identify the value of x, which is the time of discovery. So our x now is equal to 0.64536 divided by 0.40546 is equal to approximately 1.6 hours. So this is the time elapsed before the body was found, 1.6 hours. So next, we have the mixture problem. So the mixing of two fluids sometimes give rise to a linear first-order differential equation, which is the rate of change of the substance with respect to time is equals to the input rate minus the output rate. So this one is our differential model for a mixture problem. So to apply that differential model, we have here an example. A tank initially holds 100 gallons of brine solution containing 1 pound of salt. At t equals to 0, another brine containing 1 pound of salt per gallon is poured into the tank at the rate of 3 gallons per minute, while the well-stirred mixture leaves the tank at the same rate. First question is, find the amount of salt in the tank at any time t. Then, the time at which the mixture in the tank contains 2 pounds of salt. So what we know here, based on the problem, we have the volume of our tank is 100 gallons. Then, at time t equals to 0, the amount of salt or substance present on our mixture is equal to 1 pound of salt. So to apply our differential model, we need to identify first the input and output rate. So for our in, or for the input rate, we have 1 pound of salt per gallon times 3 gallons per minute. Simplifying this one, so our R in is equal to 3 pounds per minute. Then for our R out is equals to the amount of salt in our mixture. So we have A of t pounds per 100 gallon. Since we have 100 gallons of brine solution inside the tank, then the output rate of the brine is 3 gallons per minute. So simplifying this, our R out is now equal to 3 A of t over 100 pounds per minute. So substituting the value of R in and R out to our differential model, we have dA over dt equals to R in, which is 3, minus R out, which is 0.03 A of t. Rearranging this one, we have dA over dt plus 0.03 A equals to 3. So this one is our linear differential equation. So we have the value of P of t, which is 0.03, and Q of t, which is 3. So applying the method for linear differential equation, our integrating factor is e raised to integral of P of t, which is 0.03 dt. So our I now is equal to e raised to 0.03 t. So applying this one, we have integral of d of a times our integrating factor e raised to 0.03 t equals to integral of q of t, which is 3, times our integrating factor e raised to 0.03 t dt. So solving for the integrals, we have a e raised to 0.03 t is equal to the integral of 3 e raised to 0.03 t dt is equal to 100 e raised to 0.03 t plus c. Simplifying this one, we divide whole equation by e raised to 0.03 t. So this one becomes a of t is equals to 100 plus C times e raised to negative 0.03t. Now, to solve for the arbitrary constant C, we are going to apply this initial condition. At t equals to 0, the amount of the substance present in the mixture is 1 pound of salt. So we have 1 here is equals to 100 plus C e raised to negative 0.03 times 0. Solving for C, we have negative 99. So substituting that to our A of t, so the answer for letter A now is A of t equals to 100 minus 99 e raised to negative 0.03 t. So this is the amount of salt in the tank at any time t. So the next question is, find the time at which the mixture in the tank contains 2 pounds of salt. So we have the amount of substance is 2 pounds of salt, then equals 100 minus 99 e raised to negative 0.03 t. So hinanap natin is the value of t. So simplifying this one, we have e raised to negative 0.03 t is equals to 2 minus 100 is 98. Divided by negative 99, we have 98 over 99. So applying natural logarithm to the both sides of equation, we have ln e raised to negative 0.03t equals to ln of 98 over 99. Simplifying this one, we have negative 0.03t equals to ln of 98 over 99. Solving for t, we have ln of 98 over 99 divided by negative 0.03 is equals to approximately 0.338 minutes. So it takes 0.338 minutes at which the mixture in the tank contains 2 pounds of salt. So lastly, for our linear model, we have the series circuit. So the current IT and charge QT are measured in amperes and coulomb C. So to write the differential model for series circuits, we are going to apply the Kirchhoff's law. So first, we need to know the voltage drop across the components L, R, and C. So for resistance, we have the voltage drop across the resistor is IR. Then for the capacitor, we have 1 over C Q, which is Q is the charge. Then for voltage drop of the inductor, we have L di dt. So to apply the differential equation for solving a series circuits, we have here an example. An RL circuit has an EMF given in volts by 3 sine 2t and a resistance of 10 ohms, an inductance of 0.5 Henry, and an initial current of 6 amperes. So we are tasked to find the current in the circuit at any time t. So our circuit here is the voltage source, which is 3 sine 2t. Then we have the resistor of 10 ohms and the inductance of 0.5 Henry. So, based on the problem, we know that at t equals to 0, our current is 6 amperes. So, applying the Kirchhoff's law, the voltage drop across our component, we have L di over dt for the inductance plus Ri for our resistor equals to the voltage source, which is 3 sine 2t volts. So applying the value of our resistance and inductance, we have 0.5 di over dt plus 10i equals to 3 sine 2t. So dividing whole equation by 0.5, our differential equation now becomes di over dt plus 20i equals to 6 sine 2t. So this one is the differential model for our RL circuit problem. So this is a linear differential model. So our P of t here is 20 and the value of Q of t is 6 sine 2t. So solving for our integrating factor here, we have e raised to integral of P of t, which is 20 dt. So our integrating factor I now is e raised to 20 t. So applying that for finding the solution for linear differential equation, we have integral of d, our current, times the integrating factor e raised to 20t equals to integral of our qt, which is 6 sine 2t times the integrating factor e raised to 20t dt. Solving for the integrals, we have I e raised to 20t. Then the integral on the right hand side of our equation, we have to apply the integration by parts. So applying integration by parts, you'll get 30 over 100 e raised to 20t sine 2t minus 3 over 101 e raised to 20t cosine 2t plus constant of integration c. So, dividing the whole equation by e raised to 20t, we have now I of t equals to 30 over 100 sine 2t minus 3 over 101 cosine 2t plus c e raised to negative 20t. Now, to find the value of our arbitrary constant c, we're going to apply our initial condition at t equals to 0. The value of our current I is 6. So we have 6 here equals to 30 over 100 sine 2 times 0 minus 3 over 101 cosine 2 times 0 plus c e raised to negative 20 times 0. So this one equals to 0 and this one equals to 1 and this is equals to 1. So simplifying, we have 6 is equal to negative 3 over 101 plus c. Now solving for c, we have c is equal to 609 over 100 1. So this is the value for our arbitrary constant C. So now the final answer for our current in the circuit at any time t, so we have I of t is equal to 609 over 101 e raised to negative 20t plus 30 over 100 sine 2t minus 3 over 101 cosine 2t. So this is the final answer for our series circuit problem. So that's it for modeling with first order differential equation linear model. So I hope you learned from this video. Our next topic will be the nonlinear model. See you on our next discussion.